Microwave antennas, lens antennas, part 2, series on antennas and wave propagation, lecture number 5.15. Lens antennas are microwave antennas. They belong to the category of aperture antennas. They are widely used in the design of microwave communication systems like radars. Their use is mainly in combination with horn antennas. Their functioning is very much similar to lenses that are there in optics. This is second part of the presentation on lens antennas. In this part, the second part, the main focus is on artificial dielectric lens antennas and metal plate lens antennas. Two types of metal plate lenses are there. One is EPMP lenses, another is HPMP lenses. EPMP stands for E-plane metal plate and HPMP stands for H-plane metal plate. Here E stands for electric vector, H stands for magnetic vector. With this small introduction, now we move to the actual session. Dielectric lenses, artificial dielectric lenses. With a view to reduce the weight of the lenses, dielectric lenses are sometimes molded with metallic dielectric materials, which are actually artificial dielectrics. So the purpose of using metallic dielectric materials in molding lens antennas is to have a reduced weight of the antenna. Weight reduction is an advantage, and this aspect one can understand very easily when we remember that antennas are mounted in outdoors. If they are heavy, mounting them and maintaining them in their proper places against wind pressure, rain pressure, etc., becomes quite difficult. So, weight should be within limits. Artificial delay lenses was first introduced by Knock. Discrete metal particles like spheres, discs, strips, or rods of macroscopic size. They are arranged in a three-dimensional array or lattice structure to simulate the crystalline lattice of an ordinary dielectric substance. Now this substance is an artificial dielectric. It is used to mold the antenna. Usually the particles are supported by a low density dielectric medium. Metal discs or strips are generally preferable to spheres because they are lighter in weight. So artificial dielectric lenses are created mainly for their lightness to reduce their heaviness. Instead of dielectric material, artificial dielectric material is used in molding the lens. Here is shown dielectric lens antennas, that is artificial dielectric lens antennas. This is side view, right side is front view. Notice strips are arranged. One strip, another strip, another strip. These strips appear like bricks when we see from the front side. This is a plano convex lens. Here the source exists. It emits waves. These waves are of curved wavefronts. These curved wavefronts, after traveling through the dielectric lens, becomes plane wavefronts like this. Curved wavefronts are diverging wavefronts, whereas plane wavefronts are non-diverging. It implies, under the influence of lens, the directivity of the source. It has got increased. Some more points regarding artificial dielectric lenses. Radio waves from the primary antenna cause currents to flow on the spheres, making them to act as oscillating molecular dipoles. Maximum size of the metal particle should be limited to lambda by 4. To avoid resonance effects, spacing between the particles must be less than lambda to avoid diffraction effects. So resonance effects, diffraction effects, these two restrict the size of metal particle. Effective index of refraction of artificial dielectric with the conducting spheres is given by square root of 1 plus 4 pi n a cube multiplied by 1 minus 2 pi n a cube. Here n is number of spheres per meter cube. A is the radius of a sphere in meters. Artificial dielectric lenses can also be constructed by using a solid dielectric material with a controlled pattern of voids. Voids means gaps, like air bubbles. That way also one can have an artificial dielectric. Advantages of artificial dielectric lenses are given here. They have the advantage of reduced weight. From the beginning, it is being told that the purpose of artificial dielectric materials in molding lenses is to have reduced weight, which makes them suitable for use in large lenses. It means if you use artificial dielectrics, even large lenses can be designed, can be molded with low weight. They also have the advantage that the refractive index can be made to have any value over a wide range. Additionally, surface matching can be readily incorporated into the design. These are advantages. Now we move to another aspect, another type of dielectric lens, Luneberg lens. It has certain speciality, certain significance. Its significance lies in its versatility. It is a spherically symmetric delay type dielectric lens antenna with a stepped or graded index of refraction. This index of refraction increases towards the center. Here the basic point is it is a sphere. It is a sphere. It belongs to delay type lens. It is a dielectric lens. Index of refraction of the lens medium, it increases towards the center. The focal point and the feed antenna both are located over the surface of the lens. So it focuses all the radiation from the feed over a wide angle. The refractive index of the dielectric medium vary as function of radius. This variation can be expressed in the form of a relation, analytical relation. N is under square root 2 minus r by capital R square. This relation. N stands for index of refraction. R is lens radius, and small r is radial distance from the center. The versatility of this lens is several signals can be received simultaneously from different directions, and hence several signals also can be transmitted simultaneously into different directions when it is acting as a transmitting antenna. It can receive several signals while it is working as a receiving antenna. It can transmit several signals into different directions when it is acting as transmitting one. Beam steering can be done in the directions of both polar coordinates theta and phi, either by switching the receiver transmitter to different feed horns or by using single movable feed horn. Beam steering. The main beam can be oriented in different directions, either by mechanical means or by electronic means. This orientation change is called steering, beam steering. In earlier days, it was mechanical steering. Now it is all electronic steering. It can be done with Luneberg lenses without much difficulty. Now we move to another area, metal plate lenses. Earlier it is artificial dielectric lenses, now it is metal plate lenses. Two types are there, EPMP lenses and HPMP lenses. As already mentioned, EPMP stands for E-plane metal plate lens. Before going further, one point requires to be mentioned here. Basic difference between EPMP and dielectric lenses is that EPMP is a fast lens, whereas dielectric lenses, both natural and artificial dielectric lenses, are delay lenses. That difference is there. A few points regarding EPMP lens. A set of rectangular metal plates is arranged, plates parallel to each other with a uniform spacing A between them. Now the edges forming the face of the lens are cut and shaped, forming an ellipsoidal surface, the other one being a plane. One surface is ellipsoidal, another one is a plane. The spacing A of the plates should be in between lambda by 2 and lambda in order for the wave to exist only in the dominant mode. So the plates and the space between them together act as a waveguide. When it is waveguide transmission, modes come into picture, into being. Dominant mode is used widely when waveguides are used for transmission. It is the simplest possible mode. Not only that, it is associated with the smallest cutoff frequency. So certain advantages are there. That's why most of the times dominant mode propagation is preferred in waveguides. The spacing A of plates should lie in between lambda by 2 and lambda in order the wave propagation is in dominant mode. To restrict the wave propagation to dominant mode, the wave velocity in the lens with the plate spacing of A for TE10 mode. This is dominant mode. It is always more than its free space value. Equivalent index of refraction of this lens is always less than unity and depends upon frequency. The closer the spacing, the less will be the index of refraction and thinner will be the lens. But a larger refractive index results in higher reflection losses. At the upper limit of spacing, that is A equal to lambda, index of refraction is 0.866, and at the lower limit of spacing, that is A equal to lambda by 2, the refractive index is 0. Normally, the spacing is selected in such a way the index of refraction is zero point 0.5 to zero point 0.6. Notice in dielectric lenses it is around 1.5. Here it is 0.5. It is 1.5 more than 1 because they are delay lenses. Here it is 0.5 because these are fast lenses. So wave travels speedily in a fast manner in these lenses, EPMP lenses. Then they travel outside the lens medium. The index of refraction is dependent upon the frequency. Thus, these lenses are frequency sensitive, indicating that these are narrow banded devices. In this slide is shown the structure and path lengths of the rays of the wave. So let us focus on the structure. Several plates are arranged. These plates are vertical. One face formed out of the sides of the plates. This is curved. You can say this is curved. Other one is plane. A point source is here. It emits wave. Wave is electromagnetic wave. Electric vector exists in it. The arrangement is such that the electric vector in the wave is parallel to the plates. Here E is vertical, plates are also vertical. So plates are in a plane parallel to E vector. That's why this lens is called E plane. Plates are in E planes or planes containing E vector. That's why it is E plane, metal plate lens antenna. Wave travels with certain speed outside the lens. After entering into the lens medium, they start traveling with more velocity inside the medium than they traveled outside. So as the velocity is more, these lenses are called fast lenses. Now path lengths are illustrated in B. We can consider two rays. This is one ray, this is another ray, this one. This is one ray, this is another ray. Both are emitted by same source. Origin is same, starting point is the same. Point is refractive index of the medium is arranged in such a way that the ray ORP prime and ray OQ prime both cover same path length, same distance by the time they come out of the lens surface. Hence, plane wave formation takes place outside the lens medium. Zoning of EPMP lenses. Even with the index of refraction in the vicinity of 0.5 to 0.6, the thickness of lens is inconveniently large. To reduce the thickness, zoning is resorted to. So zoning is done on metal plate lenses for the purpose which is the same as the purpose for which zoning is done on dielectric lenses, to reduce the thickness. Zoning of these lenses is done to decrease the thickness and to save the weight, but this process also decreases their frequency sensitivity, resulting in increase of their bandwidth. So here is one aspect one has to keep in mind. Zoning reduces the bandwidth in case of dielectric lenses because the process of zoning makes the lens more sensitive to frequency, ultimately leading to reduction in bandwidth. But here Zoning reduces frequency sensitivity, and the zoned EPMP, E-plane metal plate lens, becomes a antenna of more bandwidth. Its typical value is 10%, which is approximately double that of unzoned lens. Zoning process is explained here. Here you can see steps, zoning steps like this. Here is shown in B is shown zoned lens, but in place of source, horn antenna is there. There is no difference between A and B. Both illustrate the same point, but in B, the place of source in A is occupied by a realistic practical source, that is horn antenna. Horn antennas, as already mentioned, in combination with lens antennas, they give tremendously beautiful performance. A few points regarding zoning of EPMP lenses. Merits: reduction in thickness and weight, reduction in frequency sensitivity, and also enhancement of bandwidth. These are all positive aspects for zoning. It can be shown bandwidth without zoning is given by 200 n by 1 minus n square delta lambda by t lambda percentage. Bandwidth in zoning becomes 50 n by 1 plus kn percentage. These two formulas use several symbols. Those symbols are explained here. Delta lambda is maximum allowable tolerance in the path difference. T lambda is thickness of the lens in free space wavelength. N is index of refraction and K is number of zones. Notice these points mentioned here pertain to EPMP. We move to another metal plate lens antenna, that is HPMP. HPMP stands for H-plane metal plate lens antenna. This lens also is made with metal plates, but in this lens, metal plates are set parallel to H vector, magnetic field vector of the wave over which these lenses work. A few points regarding HPMP lens. Before going to those points, it requires to be mentioned that HPMP lens is a delay lens. EPMP is fast, but HPMP is delay lens, like dielectric lens. To form this antenna, metal plates with which the lenses are made, they are placed parallel to H vector. So plates are parallel to H vector. That's why this lens is named as H-plane metal plate lens antenna. It's a delay lens as the wave travels with lesser velocity in the lens medium. For a point source at the focus, the required lens surface is obtained by rotating the contour of the center plate, which is a hyperbola, around its axis. A set of metal plates are arranged parallel to each other at a slanting angle, theta, with the horizontal. Here is shown the HPMP. Plates are arranged. The edges of the plates are grinned, forming a hyperboloid surface facing the source, the other face being a plane wave. This is a hyperbola. The index of refraction is 1 over cos zeta more than or equal to unity. As the refractive index is independent of frequency, it is wideband antenna. Here a gist of the properties of HPMP is given. It is slow lens, plano convex, refraction index is 1 over cos zeta, constrained refraction, Snell's law is not applicable. What is this constrained refraction? Wave, after being emitted by the source, it travels like this, like this, like this, reaches here, enters into the lens medium. There it is bent. This bending is not according to Snell's law. This bending is a forced one by the slanting angle of the metal plates. So, as it is a forced one, it is called constrained refraction. Some more points regarding a HPMP lens functioning. The electric field is normal to the plates, and thus velocity of the wave which propagates to the plates is relatively unaffected provided the plate spacing is more than lambda by 2. Notice electric vector is normal. Magnetic vector is parallel to the plates, but electric vector is normal to the plates. The direction of the rays is not affected by the refractive index, and Snell's law does not apply here. Focusing action is obtained by constraining the waves to pass between the plates. Constraining means by force. In such a manner, the path length can be increased above that in free space which are placed at slanting to increase the path length. In this lens, the most critical dimension is the path length. These lenses tend to produce unsymmetrical aperture illumination in the E plane. It is a serious drawback. Unsymmetrical aperture illumination ultimately may result in production of coma. Now, a few points regarding tolerances. What are tolerances? This topic is quite an important as far as the lens antennas are concerned. In the discussion so far conducted, it is assumed that surfaces are perfect. For example, dielectric lenses, they have one plane face, another convex face. It is assumed that a plane face is a perfect plane face, convex face is a perfect convex face, but in reality, it is impossible to have a perfect plane face or a perfect convex face or concave face. So certain variations exist, certain deviations exist over the faces from their perfect shapes. It leads to underperformance of the lens antenna. Here, right now, under tolerances, we discuss about deviations of the shapes, deviations of the refractive index, deviations of the dimensions from their designed values that are allowed without having much deterioration in the performance of lens antennas. In case of practical antennas, neither their surfaces nor their refractive indices conform perfectly to their designed values. The allowed deviations in these quantities are called tolerances. The path length variation of lambda naught over 32 RMS is specified as a tolerance to each one of thickness variations and index variations. Allowed variations, they are determined from a standard. That standard is lambda naught by 32. Lambda means wavelength, not means free space wavelength. Lambda naught by 32 RMS is the basis used for determining tolerances in thickness and index variations. If the deviations are more than the specified amounts are called tolerances. Then it leads to unwanted effects like loss of gain, increase in side lobe level, etc., which is unwanted, which may be intolerable. So here is given a table, information pertaining to dielectric lenses as well as EPMP lenses. Given thickness tolerance is 0.03 lambda naught by n minus 1 for zoned lenses. For unzoned, it is 3%. Refractive index tolerance is 3 over n t lambda percentage. For a zoned lens, it is 3 n minus 1 over n percentage for unzoned lens. In case of EPMP lenses, thickness tolerance is 0.03 lambda naught over 1 minus n. For zoned lens, it is 3% for unzoned lens. Tolerance on spacing is 3n over 1 minus n square t lambda percentage for a zoned lens. For unzoned lens, it is 3n over 1 plus n percentage. It is known, it is explained already, n stands for refractive index, t is thickness in wavelengths. Now we consider a comparison of performance of lenses with the performance of parabolic reflectors, dish antennas. Their performances are compared because they are competitors. There exist several applications where either one can be used without much difficulty. Comparison 1. Parabolic reflectors are simple to design as they involve only one surface, and also due to their functioning being dependent on simple elementary laws of geometrical optics. On the other hand, lenses are highly complicated structures. However, it is possible to achieve some special benefits like having a scanning angle which is more than the beam width with the lenses. So here the point is, parabolic reflectors are simpler to design when compared to lenses. Lenses are complicated structures. Second point, the tolerances on the lens surface shape are more lenient than that of the reflector. For the same effect due to change either in thickness delta t or refractive index delta n of the lenses, the deviation of the surface of the paraboloid can only be half as large, placing a severe requirement of accuracy for a large reflectors at high frequencies. It implies deviations in thickness, deviations in refractive index, deviations in irregularities of the surface. They are more tolerable. In general, deviations are more tolerable in case of lenses than in the case of reflectors. Third point, the gain of the lens antenna is usually 1 or 2 decibels less than that of reflector, but with the use of surface matching and extended feed horn, it is possible to make gain of the lens more than that of the reflector. Gain wise, in general, lenses are slightly poorer. However, with adopting surface matching and extended feed horn, using extended feed horn, it is possible to increase the gain of lenses to the gain level of reflectors. Fourth point, with the lenses, relatively large amount of warping or twisting can be tolerated. Also, the lens antennas have considerably less rearward radiation than reflector antennas. Fifth point, without any serious ill effects, lens axis can be tilted considerable angle with respect to the axis through primary antenna and the center of the lens. After comparison, now we consider advantages of lenses. In general, the advantages of lenses are mentioned in comparison with the parabolic reflectors as they are competitors. This aspect has already been mentioned earlier, and the relative performance of lens antennas, it is already given in comparison with reflectors. Here we consider advantages two relative to parabolic reflectors. One major advantage with lens antennas is the absence of aperture blockage. They don't require primary antenna mount to be placed, obstructing the radiation. Two, the lens is capable of scanning the beam over a wide angle. Constrained metal plate lens antennas are capable of wide scan angles when compared to parabolic reflectors. Three, in addition, the dielectric lenses have greater design tolerances when compared to parabolic reflectors. Third point has already been mentioned. Deviations are more tolerable in case of lenses than in case of reflector antennas. There exist certain drawbacks for lens antennas. These are bulky, expensive, difficult to design. Provision of mechanical support of lens antenna is usually a more serious problem than to a reflector. Second point, there exists a mismatch between primary antenna and its feed line or guide. Even though primary antenna interferes not with the plane wave leaving the aperture, the energy reflected from the lens surface may spoil the match of primary antenna with its feed. This is another drawback of lens. 3. Lenses are usually less efficient than comparable reflector antennas. It is because of the absorption when propagation through the lens medium, and also due to reflections from the two lens surfaces. 4. In addition to a zoned lens, there exists additional undesired scattering from the zoning steps. With this, we come to an end to the present session. That is the second part of the presentation on lens antennas. This session is mainly on artificial dielectric lenses and metal plate lenses or lens antennas. Hope this session is useful to you. We meet again in another session with a new topic very soon.